Thank you for the introduction. So before starting, I'd like to give a quick shout out to my co-authors, great folks without whom I couldn't have done this project. So this is a publicly available face recognizer, which we will call A. It is biased, and we know this because it has not detected a face where there is a face, and it has detected a face where there is a mask. In her TED Talk, Joy goes on to describe that the source of this bias is insufficient training examples with a variety of skin tones. So that seems solvable. Imagine we got more data, and we created a better classifier, B. Could you tell these classifiers apart? How? And what I mean by how is, are we simply observing classifications, or are we doing something explanatory? And when? And what I mean by when is, can we catch this during testing before we deploy this? So in the last slide, we were being colloquial in terms of what we considered a bias. Data scientists have devised a number of different fairness definitions and can optimize relative to them. Since these techniques rely on a definition, they're normative. However, we want to know if statistically fairer classifiers will be perceived as fairer by people. To do this, we conducted a survey, which is inherently descriptive, as each person could be applying a different definition of fairness. But their perception depends on how we explain it to them. Explanations are the window for human scrutiny and intervention of the ML models to ensure their fairness. But not all explanations are equal. For example, are some explanations inherently more or less fair? What is the best style for different regions of feature space and different people? So now I want to go over a high-level view of what we did. And as I go through this figure, don't worry too much about how each piece works. Instead, focus on how they connect. So we started with some data, which might have some bias present. To reduce that bias, we used a debiasing technique, which runs as a preprocess and transforms the data. So now we have two data sets, which are similar, but not the same. We then trained two classifiers based on each data set, which we will call raw and processed. Again, these classifiers are similar, but not the same. Next, we programmatically generated 4 types of explanations, denoted by the 4 different colors of arrows on the figure, for each test sample, of which we have around 1,000, which is why we have the black dots. Remember, we were interested in human perception, and 4,000 explanations is too many to do a survey with, so we chose a smaller set to study. Last, we ran a survey to measure how humans perceive decisions from the classifiers. Participants rated agreement with the prompt shown here, how the software made the prediction was fair. So now we understand the end-to-end plan. Let's make each piece more concrete, starting with the data. Decision support software is in use in courtrooms today to inform sentencing and bail. In DSS settings, the human is providing the final decision, but among the data available is ML output, which might potentially be biased. Note that these systems are based on proprietary methods and data, but we were able to build our own system based on data from a watchdog group. This data comes from Broward County, where many court records are public, providing a ground truth on people who commit another crime within these 2 years. Note that ProPublica's goal was to investigate the commercial systems, while ours was to use their data to train a DSS similar to those in use today. I'll skip the specifics on debiasing and simply remind you that it operates as a preprocess that transforms the data. We were interested in the data processing factor because data scientists have devised many techniques to increase model fairness in a statistical sense. However, there's been surprisingly little study of whether or not these models are perceived as more fair by people. So using both data sets, we trained 2 classifiers. Both use logistic regression, so they have a linear decision boundary. Armed with the classifier, we programmatically generated textual explanations based on templates from recent work in Chi. We studied the explanation factor because it is the interface for the human in the loop to scrutinize the model, and we were interested to know if some explanations reveal model fairness better. The figures in the next couple of slides are from our supplementary materials if you'd like to spend more time with them. So input influence explanations are global, meaning that they will generate the same or similar explanations for all input samples. The input influence-based explanation describes the impact of the various feature values have on the decision. The bold-faced lines here highlight the categories containing the feature values for which the explanation was generated. So now, to read an individual line, let's jump down to the prior convictions feature. As one might expect, if a defendant has greater than 10 prior convictions, it is positive evidence that they may reoffend, which is denoted by the plus sign. The fact that it is strong positive evidence is denoted by the large number of plus signs. Conversely, if a defendant has no prior convictions, we might expect that to be strong negative evidence that they may reoffend. And we see that as the case with a large number of negative signs. Now, if a feature has a coefficient of 0, that means its impact on the decision is slim to none. Note that participants only worked with one of the classifiers and saw one type of explanation, but I wanted to show you a side-by-side to illustrate the effect of the preprocessing. So here we can see the effect of the debiasing step, where in the process classifier, both races have a 0 coefficient. Last, by visual scan, we can see that the classifiers are similar. The strings are of roughly equal length, and there are no large sign changes. Demographic-based explanations are also global. They describe how the training data is distributed. Again, we can see the effect of the debiasing step in the process data classifier. Further, we can see with a visual scan, the data has moved around, but not by a large amount, plus or minus a few percent. In the sensitivity-based explanation, we modify the individual features, one at a time, and see if the decision changes. If it does, we report a line like the one highlighted. This defendant has juvenile priors. However, had they not had those priors, the decision would have changed. Note that each individual will have different sensitivities, and so this type of explanation is local. Case-based explanations are also local. Here we depart from the BIN's template, since their approach was to do a one nearest neighbor search. In our case, our feature space was small compared to the size of the data set, so we were often able to find exact feature matches. If matches are found, we report on the distribution of their labels. Otherwise, we fall back on one nearest neighbor search as from BINs. Okay, so now we're here in the diagram with too many explanations, and we need to choose a subset to study in our survey. In order to do that sampling process, we consulted a definition. Discrimination, loosely stated, is present if we change the protected variable and the decision changes. Discrimination can lead to disparate impact, which can lead to disparate treatment, which is a legal term meaning that the discrimination is both too severe and demonstrable, and may result in a lawsuit. So a sharp-eyed viewer might have noticed this line in the sensitivity-based explanation from earlier. It illustrates that this person has been disparately impacted because the decision changes if we change only their race. We were interested in studying the disparate impact factor because it is important that these cases are caught before release. Notably, they're pretty rare in our data set, so we oversampled these individuals. We showed each participant 6 cases, 2 disparately impacted and 4 non, in a random order. Finally, we're ready to combine our ingredients and run a survey. In this paper, we report on our participants' answers to their agreement with the statement, how the software made the decision was fair. We did the survey with Amazon Mechanical Turk crowd workers, and we asked them about some important individual difference factors, but the one I will focus on in this talk is trust in ML. Okay, let's jump into some results. So we'll spend a little bit of time with this image, so I want to help you read it. At the bottom, we have a category for each explanation type. Each explanation type has 4 box plots. The ratings for the raw data classifier are shown with the circles, and for the process data classifier, the triangles. Ratings for the disparately impacted cases are shown in the blue dashed lines, as opposed to the non-impact cases, which are the red solid lines. So for the data processing factor, the processed classifier was considered significantly fairer than the raw classifier, which we can see because the triangles are above the circles of same color, and I've highlighted an example in the black box. From this, we can infer that improving the statistical fairness via debiasing also improves the perceived fairness. Next, the disparately impacted decisions were rated significantly less fair than the others, which we can see because the blue marks are below the red marks of the same shape. And again, I've highlighted an example in the black box here. This indicates that explanation can help testers catch these important cases. The last result on this figure, the difference between the red and blue marks is greater for local explanations, which we've highlighted in brown. And this shows us that local explanations are more effective at revealing disparate impact. So the last result I want to show you is that participants with high trust in ML rated the decisions as more fair. This effect was stronger when they were given a global explanation, which we've highlighted in purple. This illustrates the importance of understanding the right individual factors when designing and choosing explanations. So to clarify some of these described issues, consider the following geometric interpretation. On the figure, positive examples are marked with a blue plus, while negative examples are marked with a red minus. The decision boundary is the thick black line. Now, suppose a user requests an explanation for an instance at either of the two question marks. Input influence-based explanations attempt to expose feature coefficients, and thus to describe the decision boundary itself, which does not change with samples, and is thus global. Demographic explanations instead describe the distribution of the training data, in other words, where these pluses and minuses are positioned. Note that this also does not change per sample, and is thus global, meaning that each point will get the same explanation up to highlighting. On the other hand, local explanations will change given different individuals. Sensitivity-based explanations vary features one at a time, checking to see if the decision changes. Geometrically, this is like projecting an axis-aligned line from the point until it collides with the decision boundary. Each individual will have different sensitivities. For example, we might expect the question mark near the decision boundary to have many sensitivities, as small changes might push it over to the other side. Conversely, the question mark far from the boundary might have a small, or possibly even empty, set of sensitivities. Case-based explanation is also local and corresponds to expanding a circle around an individual and reporting on the distribution of its contents. Consider that a circle around the question mark near the decision boundary is more likely to contain examples of the opposite label than the question mark that is further away. So to summarize, global fairness issues arise from a bad decision boundary, which can be caused by a number of factors, such as the insufficiency of data in the facial recognition example from earlier. On the other hand, local fairness issues arise because where the sample is in feature space matters. To clarify, training processes typically optimize a global objective, which causes the fairness of some decisions to be sacrificed. We examined the following three variables. Data processing, and we did this because debiasing techniques are understudied from a human perspective. The second factor we examined was explanation, and we did this because explanations allow a view of the classifier which can reveal fairness. The third factor we studied was disparate impact, and we did this because catching discriminatory decisions is important due to ethics as well as the legal risks. So key takeaways from our paper, starting with the empirical results. First, increase in the statistical fairness seems to be correlated with an increase in the perceived fairness in participants. This indicates that debiasing sort of works from a human perspective. Second, disparately impacted decisions were rated less fair, indicating that these decisions should be scrutinized. Third, local explanation is more effective at revealing disparate impact, indicating their usefulness in identifying these key individuals. Moving on to some lessons learned from our methodology. First, we generated explanations programmatically, and this insight led us to conclude that combining global explanations with local ones could be important. Further, it might also be important to explain both the process and the data. Next, we found individual differences to be extremely important. So I showed you the image of trust in ML, and I also want to note that we observed no significant effects in the data until we incorporated the participant's position on using race as a feature in ML decision making. Last, we wish to bring the human view to debiasing. There are a lot of debiasing approaches, and there are very few studies investigating how humans perceive their results. However, we would like to go beyond this and issue a call for data scientists and HCI researchers to work more closely together moving forward. Thank you for your attention.
Thank you for the quick presentation. It's time for questions.
Thanks for a really interesting talk. Here, yeah.
Oh, thank you.
It really reveals a bunch of things beyond what a bunch of the presentation considered. But I wonder to what extent the domain might have some implication in that case, because the case of conviction, has a really very broad media coverage. And it was exactly used as a case to stress that AI technologies may not be really good, and there's a lot of press coverage stressing that what should be good. Mm-hmm. Wouldn't it be kind of more reliable to get a case where it's not really clear what is just, what is not just, And only the explanation, not the press coverage, would really guide the Turkers in their judgment. Because I think that this is a really very hot example to kind of be completely unbiased.
That's fair. So internally, so first thanks for the question. Internally, we discussed several other cases that we might have looked at. One was we considered using synthetic data. The weakness of that approach is that, your participants aren't bringing any biases to the table. They don't have beliefs about, squares versus triangles or things like that. And there are a couple of other data corpuses we might have used. For example, the German credit score data set. That's another biased data set we could have used. But the problem with that sort of output is that's predicting whether or not the machine believes this person will earn, I believe it's over $50,000 or $100,000, whatever. And that's not visceral, right? Ultimately, it doesn't matter whether or not that prediction is true or not to a person viewing that explanation. Whereas once you're possibly throwing someone in prison, it raises the stakes a lot more. So that's kind of why we chose this particular use case, if that answers your question.
Hi, thanks. One of my questions that came up is, I was interested in the way that you looked into the effect of the explanations and how that was revealing to even untrained human reader about the fairness bias of the model. But in the experience that I have of these types of models, they tend not to use something that's quite as obvious as race. They will use something that's heavily correlated, since they're not generally allowed to include something that obvious.
Sure.
So did you look into whether, like, in reality, a model like this would say something more like, they were more likely to have recidivism problems because they live in zip codes 90211
Sure.
or something like that. So did you do any investigation with whether humans were able to interpret that, or?
We did not. I don't believe the COMPAS data has zip code information or much that I would really say with a lot of certainty is strongly correlated to race. I might be wrong on that. It's been a while since I've looked into this data corpus, but I'm not sure we have a great proxy variable to use in that way in that data set.
Okay.